As with our free vibration case, most structures exhibit some degree of damping, so we will now consider the case where a force system features damping in its equation of motion. The equation of motion is now given by the acceleration or inertial term plus the damping force term plus the stiffness term, and that's set equal to the forcing function. Our mass spring damper system can now be drawn with all of its features. If we now divide our equation of motion by m and note that c over m is equal to 2 zeta omega n, we have for our equation of motion the acceleration plus 2 times zeta omega n times by the velocity plus the square of the natural frequency times by the displacement, and that's set equal to p naught over m sine omega t. Because this is now an inhomogeneous ordinary differential equation, we need to derive again the complementary function and the particular integral. For the complementary function, we have already derived this looking at our free vibrations problems in video 4. The complementary function is simply the solution to the homogeneous version of equation 1. That is to say that uc of t is equal to a times cosine of the damped natural frequency plus b times sine with the damped natural frequency times by the exponential function of minus zeta with the natural frequency times t. For the particular integral, to account for the fact that the response may not be in phase with the loading, we include both sine and cosine terms in our proposed particular integral function. So, our proposed particular integral, EPT, is equal to g1 cosine omega t plus g2 sine omega t. We can then differentiate this, firstly to obtain the velocity, and that gives us minus omega g1 sine omega t plus omega g2 cosine omega t, and the acceleration, which is equal to minus omega squared g1 cosine omega t minus omega squared g2 sine omega t. Substituting this then into the equation of motion, we now have minus omega squared g1 cosine capital omega t minus omega squared g2 sine capital omega t minus 2 times zeta omega n capital omega g1 sine capital omega t plus 2 times zeta omega n capital omega g2 cosine omega t plus the natural frequency squared times by g1 cosine omega t plus the natural frequency squared g2 sine capital omega t minus p naught over m times by sine capital omega t, and that's set equal to 0. Term by term, this first collection of terms is the acceleration. This second collection of terms is 2 times zeta omega n times by the velocity, and this term here is the natural frequency squared times by the displacement. If we now collect sine and cosine terms, i.e. factorise, then we have minus g1 omega squared plus g2 omega times by 2 times zeta omega n plus g1 omega n squared, all times by cosine capital omega t, plus minus g2 omega squared minus g1 capital omega 2 times zeta omega n plus g2 omega n squared minus p naught over m times by sine omega t. Simplifying this expression further, we then have omega n squared minus capital omega squared times by g1 plus 2 times omega n capital omega g2 times by cosine omega t plus minus 2 zeta omega n times by capital omega g1 plus omega n squared minus capital omega times by g2 minus p naught over m times by sine omega t, and that's equal to 0. If we now divide this expression by the natural frequency squared, and note that stiffness can be expressed as the natural frequency squared times by m, then we can say that our expression can be further simplified as 1 minus capital omega squared over the natural frequency squared times by g1 plus 2 times zeta capital omega over the natural frequency times by g2, and that's all times cosine omega t plus minus 2 times zeta omega over the natural frequency times by g1 plus 1 minus capital omega squared over the natural frequency times by G2 minus P naught over K times by sine omega t, and that's equal to 0. As before, we now define beta equal to capital omega over omega n, and in particular, equation 6 is only satisfied when the terms in the square brackets sum to 0. So substituting in for beta and saying that the terms in square brackets must be 0, we end up with 1 minus beta squared times by G1 plus 2 times by zeta beta G2 minus 2 times by zeta beta G1 plus 1 minus beta squared times by G2. This first equation we've said is equal to 0, and the second equation is equal to P naught over K. This then is a system of equations, and it may be written in matrix form. 1 minus beta squared, 2 zeta beta, minus 2 zeta beta, 1 minus beta squared, with the column vector G1 and G2. Set equal to 0 and P naught over K. We now then just need to solve for G1 and G2. So we multiply the adjoint matrix by the determinant to have 1 minus beta squared all squared plus 2 times zeta beta all squared times by 1 minus beta squared minus 2 zeta beta, 2 zeta beta, and 1 minus beta squared times by this column vector, giving solutions for G1 and G2. Therefore, G1 is equal to P naught over K times by minus 2 zeta beta, 1 minus beta squared all squared plus 2 times zeta beta squared. G2 is equal to P naught over K times by 1 minus beta squared times by 1 minus beta squared all squared plus 2 times zeta beta all squared. If we then substitute this back, G1 and G2, into equation 4, which is up here, then we end up with, for the particular integral u p of t, P naught over K times by this common factor 1 over 1 minus beta squared all squared plus 2 zeta beta squared times by 1 minus beta squared times by sine capital omega t minus 2 zeta beta times by cosine omega t. The total solution then, ut, is just then the complementary function plus particular integral. So we have a times cosine omega dt plus b times by sine omega dt times by the exponential of minus zeta omega nt plus our particular integral p0 over k times by 1 over 1 minus beta squared all squared plus 2 zeta beta all squared times by 1 minus beta squared sine omega t minus 2 zeta beta cosine omega t. As before with damped vibrations or forced vibrations, we have a transient component and we have our steady state component, noting that the transient component features functions which are functions of the damped natural frequency, and the steady state component features functions which are functions of the forcing frequency. So we can see here we've got capital omegas wherever we have time, whereas in this part we've got the damped natural frequency everywhere we have time.